In this lesson, we will delve into the principles of milling processes and the application of tool systems as covered in Project 1. In this section, we will explore the fundamental principles of milling, including key concepts such as milling motion and milling elements. We will also learn about the application of tool systems, such as tool selection and the geometric angles of tools. Through the study of these topics, you will gain a comprehensive and in-depth understanding of milling processes, laying a solid foundation for future practical operations and professional learning. In the field of metal cutting, milling is a very important machining method. Next, we will study in detail the principles of milling processes and the application of tool systems. During milling, there is relative motion between the tool and the workpiece, primarily consisting of the main motion and the feed motion. The main motion is the rotational movement of the tool, which enables the tool to cut the workpiece and is the most power-consuming motion in milling. For example, on a vertical milling machine, the high-speed rotation of the milling cutter constitutes the main motion. The speed of the main motion is expressed as the cutting speed Vc, calculated using the formula. Vc is pi dn over 1000. Here, d is the diameter of the milling cutter in millimeter, and n is the rotational speed of the milling cutter in revolutions per minute. The derivation of this formula is quite simple. When the milling cutter completes one full rotation, the distance traveled by the cutting edge is the circumference of the circle, pi d. Since the milling cutter rotates n times per minute, the distance traveled by the cutting edge per minute is pi dn. Converting the units to meters per minute gives us the cutting speed Vc. The feed motion continuously advances the workpiece into the tool, enabling continuous cutting. The feed motion can be linear, such as the longitudinal, transverse, and vertical movements of the work table. It can also be circular, such as the rotational feed of the workpiece on certain milling machines. The magnitude of the feed motion is measured by the feed rate, commonly expressed as feed per tooth, Fz in millimeters per tooth, feed per revolution F in millimeters per revolution, and the feed speed Vf in millimeters per minute. Their relationship is given by Vf equals Fn equals Fz Zn, where Z is the number of teeth on the milling cutter. The derivation of this formula is based on the following logic. The feed per tooth Fz represents the distance the workpiece moves relative to the tool for each tooth the cutter passes. With Z teeth on the cutter, the distance the workpiece moves for one full rotation of the cutter is Fzz. Since the cutter rotates n times per minute, the feed speed Vf equals Fzz. The feed per revolution F is the distance the workpiece moves relative to the tool for each full rotation of the cutter, so F equals Fzz. Consequently, Vf equals Fn. Milling elements. Milling elements include the milling width AE, milling depth AP, and cutting layer parameters. The milling width AE refers to the dimension of the cutting layer measured perpendicular to the axis of the milling cutter, which is the cutting range of the cutter in the width direction of the workpiece. The milling depth AP refers to the dimension of the cutting layer measured parallel to the axis of the milling cutter, which is the depth to which the cutter penetrates the workpiece. The cutting layer parameters mainly include the nominal cutting thickness HD and the nominal cutting width BD. The nominal cutting thickness HD refers to the perpendicular distance between the trajectories of the main cutting edges of two adjacent teeth. The calculation formula is HD equals Fz times sin Kr. Kr, the rake angle of the main cutting edge of the milling cutter. This formula is derived based on geometric relationships. From the geometry of the cutting layer, it can be seen that the projection of the feed per tooth Fz in the direction perpendicular to the main cutting edge is the nominal cutting thickness HD. Sin Kr is the proportional coefficient of this projection. The nominal cutting width BD refers to the dimension of the cutting layer measured along the direction of the main cutting edge. Its size is related to the milling depth upon the rake angle Kr. The calculation formula is BD equals AP divided by sine ke R. This formula is also derived based on geometric relationships. According to the geometry of the cutting layer, there is a proportional relationship of sin kr between AP and BD. Application of tool systems. The tool system plays a crucial role in milling operations, including the selection of tools and the geometric angles of the tools. Tool selection. The selection of tools requires consideration of multiple factors, such as the workpiece material, processing requirements, and machining method. For different workpiece materials, it is important to choose the appropriate tool material. For instance, when machining aluminum alloys, high-speed steel or carbide tools are generally selected. In contrast, when machining high-hardness alloy steels, carbide tools are more suitable. There are also many types of tools, such as cylindrical milling cutters, end mills, and vertical milling cutters. Cylindrical milling cutters are primarily used for machining flat surfaces. End mills can be used to machine flat surfaces, stepped surfaces, and more. Vertical milling cutters are commonly used for machining slots, contours, and similar features. Geometric angles of tools. The geometric angles of a tool significantly affect its cutting performance. These angles mainly include the rake angle gamma 0, clearance angle alpha 0, main cutting edge angle Kr, secondary cutting edge angle Kr, and the inclination angle lambdas. The rake angle gamma 0 is the angle measured between the rake face and the reference plane in the orthogonal plane. Increasing the rake angle can make the cutting edge sharper and reduce the cutting force, but it will decrease the strength of the tool. Generally, when machining plastic materials, a larger rake angle can be chosen to reduce cutting force and cutting heat. When machining brittle materials, a smaller rake angle should be selected to ensure the strength of the tool. The clearance angle alpha 0 is the angle measured between the flank face and the cutting plane in the orthogonal plane. The purpose of the clearance angle is to reduce friction between the flank face and the machined surface of the workpiece. If the clearance angle is too large, the strength of the tool will decrease. If it is too small, friction will increase. Typically, a smaller clearance angle is chosen for rough machining, while a larger clearance angle is selected for finish machining. The main cutting edge angle, Kr, is the angle measured between the projection of the main cutting edge on the reference plane and the feed direction. The size of the main cutting edge angle affects the distribution of cutting forces and the durability of the tool. Reducing the main cutting edge angle can increase the cutting width and decrease the cutting thickness, which is beneficial for improving the tool's durability, but it will increase the radial cutting force. The secondary cutting edge angle Kr joint is the angle measured between the projection of the secondary cutting edge on the reference plane and the opposite direction of the feed motion. The purpose of the secondary cutting edge angle is to reduce friction between the secondary cutting edge and the machined surface, preventing vibration. The secondary cutting edge angle is generally set to a smaller value. The inclination angle lambdas is the angle measured between the main cutting edge and the reference plane in the cutting plane. The inclination angle can control the flow direction of the chips. When lambdas is greater than 0, the chips flow towards the surface to be machined. When lambdas is less than 0, the chips flow towards the machined surface. Additionally, the inclination angle also affects the strength of the tool and the direction of the cutting force. The craftsmanship in precision milling. In precision milling, there are almost stringent requirements for the dynamic balance and clamping accuracy of the tool system. Poor dynamic balance of the tool system can lead to vibrations during the milling process, affecting the quality of the machined surface and reducing the durability of the tool. For example, in the precision machining of aerospace components, even a slight vibration can result in dimensional deviations, affecting the performance and the lifespan of the parts. Therefore, before performing precision milling, it is essential to conduct rigorous dynamic balance testing and adjustments on the tool system to ensure stability during high-speed rotation. The clamping accuracy of the tool is also crucial. Inaccurate clamping can cause the actual cutting parameters of the tool to deviate from the theoretical parameters, affecting machining accuracy. For instance, in mold manufacturing, a high-precision mold cavity requires extremely high machining accuracy. Even a slight deviation in tool clamping can result in the mold being scrapped. This requires us to meticulously attend to every detail during the operation, striving for the highest excellence in machining quality and cultivating a spirit of craftsmanship that seeks perfection. In this lesson, we learned about the principles of milling and the application of tool systems. We first explored milling movements, including the primary motion and feed motion, and mastered the calculation methods for parameters such as cutting speed and feed rate. Then, we studied milling elements such as milling width, milling depth, and cutting layer parameters. We also explored the application of tool systems, including the selection of tools and their geometric angles, as well as their impact on cutting performance. Finally, through the stringent requirements for dynamic balance and clamping accuracy of tool systems in precision milling, we recognized the importance of the spirit of craftsmanship that strives for perfection in milling processes. I hope that in your future studies and practice, you will be able to skillfully apply this knowledge and cultivate a meticulous and rigorous work attitude.